Seminar series, our weekly seminar series, and today it's my pleasure to do the announcements. Actually, I know several of our professors are not here. Today's seminar will be on an interesting topic on the use of ground penetrating radar for assessing compaction and monitoring compaction levels of asphalt concrete compaction. I know that our speaker, a PhD student and a candidate, coming up candidate PengCheng, Shangwan, has been here for some time with us, since 2010. I know he and we've worked on some projects even outside together. He's started with Professor Al-Qadi on working on the ground penetrating radar, and he's done some quite a work actually on density measurements. Now his talk is going to be on innovative approach for asphalt pavement compaction monitoring using ground penetrating radar. This is a topic that's picking up quite recently actually. I noticed that collecting density information of asphalt concrete compaction process is a recent interesting research area. I heard this from some others recently, and I know you've done quite a work on this. He graduated from Southeast University from the Transportation Engineering Department, PengCheng, in 2008. And since that time, actually, he arrived at UFI and got his MS from us, master's from us in 2010. And he's continuing on to do his PhD on this topic. So he has some good, interesting material to share with us today. Without further ado, I will turn it over to PengCheng. Thanks.
Okay, thanks, Professor Tutumlo, for the nice introduction. My topic today is an innovative approach for asphalt pavement compaction monitoring using ground penetrating radar. And before I start, I would like to acknowledge the co-authors of this study, which is Professor Imad Al-Qadi, who is my advisor, Professor Len, who is a previous PhD student in our group, and now he is in Hong Kong Polytech University as an assistant professor, and Professor Schmidt and Professor Fahim, who are professors in University of Wisconsin, Platteville. I'd like to divide my presentation into several parts, including introduction and theory about ground penetrating radar. And then I'm going to talk about laboratory tests, including the result analysis and also the algorithm development. Then I'm going to talk about field applications. Then a summary will follow up. We'll conclude this presentation. As we all know that asphalt pavement density is critical QC/QA parameter. Probably is the most important QC/QA parameter in asphalt pavement construction. And proper density is essential to achieve long-lasting pavement performance and to reduce the cost of maintenance and rehabilitation. And during the pavement construction, the densification of asphalt mixture is achieved by compaction. So it would be beneficial to develop a technique that can monitor the density change after each compaction pass. However, no current technique can really achieve that. Here lists several techniques for QC/QA methods. For example, the coring method is destructive and it's time consuming, and it can only give you the information after the construction. So no information can be provided during the compaction. And nuclear density gauge, it uses a radioactive material, and so it requires certain licensing to operate and storage. And the biggest limitation is it's a spot test, so it only provides you the density information at certain discrete locations. And then people developed a new non-nuclear density gauge, and it doesn't use radioactive material. However, it's still a spot test, which means it's still collecting discrete location densities at discrete locations. And also it requires surface contact. The reason why I say this is a limitation because we want to achieve continuous and rapid monitoring. So if the tool requires surface contact, it cannot achieve the goal I defined. And then intelligent compaction is a very hot topic now. However, the limitation of this method is it's based on the stiffness of the whole pavement system. And we know that the stiffness changes with the temperature and also subgrade conditions. So in that case, any measured stiffness increase may not be caused by the increase in density. Instead, it might be caused by the temperature drop or the subgrade condition change. So we want to find a way to overcome all these limitations and to achieve the real-time and continuous and rapid compaction monitoring. So we turn to the GPR method. The GPR, the ground penetrating radar or GPR, has been applied for thickness and density measurement and defects detection of asphalt pavement for many years. Of course, the density prediction is just developed. And the main advantage of this method is it's non-destructive, it's non-contacting with the surface, and it provides continuous measurement, and it provides high coverage area, and it's very rapid because it can collect data at highway speed without any interruption to traffic. So it's a promising technique for compaction monitoring. However, the biggest challenge here is GPR signal is very sensitive to water, and I'll explain why in the slides later. And the effect of this roller sprayed water on GPR signal is unknown. As we all know that during the compaction, the compactor will spray some water on the roller to prevent the sticking or the picking up of the asphalt particles. And this water is having big impact on GPR signal. So we have achieved thickness and density measurement using GPR. Now the question is, can we apply the results or the theories used for density measurement and take one step further to monitor density during the compaction? And as I said, the biggest challenge here is water, and we are going to tackle with this water problem. And so far, actually, for all the researchers who's doing GPR research, it's very hard to deal with water. So not too many, actually there's no literature I found doing the water, measuring the pavement with water. All the GPR tests, they require the pavement to be dry, or at least 3 days no raining, or maybe 1 week no raining, depends on the states and the specifications. So this challenge somehow defines our research objectives, which is first we want to investigate this effect of roller sprayed water on GPR signal during compaction. And then hopefully we can develop a data processing technique to eliminate this effect of water. And then we are going to validate this effectiveness of using GPR, both for validate the hardware and the software part in the application of compaction monitoring. Let's first look at how GPR works. As you can see in this picture, the 2 orange boxes are the most critical part of GPR system, which is the antenna. And in each orange box, there are 2 antennas. One is transmitting antenna, one is receiving antenna. The transmitting antenna sends out this blue color pulse-shaped electromagnetic wave, or EM wave, into the ground. And when the EM wave encounters interfaces, such as the surface of the AC layer or the bottom of this AC layer, part of the energy will be reflected back, which is here the red pulse-shaped EM wave. And it will be received by the receiving antenna inside this box. And the signal will be transferred to this data collection unit so you can get the GPR signals. And the GPS and the DMI, which is distance measuring instrument, can integrate the GPR signal with the distance or with the locations. So you know so like you know the places each GPR scan corresponded to. And in order to understand the GPR principle, we also need to understand the EM properties of materials. There are several properties that affect the GPR signal. However, the most critical property is called relative permittivity or dielectric constant, and we'll call it dielectric constant in this presentation. It's defined as the ratio of electrical energy stored in a material by applied voltage relative to that stored in a vacuum. And this equation tells you how the dielectric constant of a material was calculated, which is the permittivity of the material relative to the permittivity of vacuum. This table lists several typical values of materials, the dielectric constant values. For example, as we said, it's relative, it's normalized to vacuum. So the air has a dielectric constant of 1, and asphalt concrete has a dielectric constant of 3 to 10, and water has a 81. That's why the water has a big impact on GPR signal. And here I want to mention that there's a relation between the dielectric constant of a material and its density. So the denser the asphalt concrete is, the higher value of dielectric constant is. So that's also the principle we can use it to predict density or doing the density monitoring. And this figure shows you how the EM wave, the GPR wave, propagates within the pavement. As you can see, there will be a surface reflection, there will be a bottom reflection, there will be a reflection here. And we are only interested in this part of the signal because it reflects the property of this AC surface layer. We are not interested in anything below that. And there's an equation to calculate the dielectric constant of the AC layer. As you can see here, this AP is the amplitude of the incident wave, which can be collected by putting a metal plate underneath the antenna, because the metal plate is a perfect reflector, so you can know what you are sending out. And this A0 is the amplitude of GPR wave reflection at the pavement surface. So we are totally relying on this amplitude to calculate the dielectric constant of AC layer. And we can reorganize this equation into this format. In this format, basically, we can know that when the dielectric constant increases, this amplitude will also increase. And the problem is the density of asphalt pavement is what we are interested in. So we need to get the density based on this dielectric constant. And there are a lot of models describe this relation. And here I'm going to show you one of the models, which is called ALR model, which is developed in our group. And this GMB is the density of the asphalt pavement. This epsilon AC is the dielectric constant of the top surface. And there are a lot of parameters here, but they are usually known. So by using this equation, you can get the density based on the dielectric constant. And in our application, it's we need to reorganize this. But these whole three equations tell us that the principle of density compaction monitoring is that when the compactor passes the asphalt mixture, the density increases. So based on this equation, when the density increases, this dielectric constant will also increase. When the dielectric constant increases, the surface reflection amplitude will also increase. So when you place an antenna here, and when the compactor passes and passes and passes, you will find that this surface reflection amplitude increase and increase and increase. So that's the principle that's how we can monitor the compaction status. However, these three equations are all based on dry pavement. As we said, the biggest challenge is water. So we are going to investigate how the water affects the signal. And we did this laboratory test outside the TOL. And there's a test section made of different thicknesses and densities. And we choose one lane, which is made of limestone aggregate and PG64 22 asphalt binder. We use 2 GHz L-coupled antenna. There are different frequencies you can choose for antennas, and this is the most common one for L-coupled system. By L-coupled, I mean you don't need the antenna in contact with the surface. So we can collect data very quickly. And the pavement temperature is pretty high because we did this test in last summer. And we want to choose the hottest day so that the any water we sprayed on the pavement can evaporate very quickly. And then this is the test procedure. We first collect data on dry pavement, which is pretty normal. We did this like the same thing for all the GPR tests. Then we did something special, which is we spray some water using this nozzle sprayer and spray them evenly on this square area. And the amount of water is 250 milliliquid. We get this number based on the calculation of based on some specifications of compactor manufacturer to simulate how much water will be sprayed during compaction. Then we collect this data after spraying water at 1 minute intervals until the pavement was completely dry. And I found usually it takes around 1 hour for the pavement to be completely dry. So in that case, we can capture the changes in GPR signal due to the surface water variation. And I'm going to show you the result. So as expected, after spraying water, the surface reflection amplitude increased. As you can see in this figure, the blue curve is the data collected on dry pavement. This red curve is the data collected from wet pavement. So it increased a little bit. This is as expected, but this also tells us that we cannot use the traditional GPR data processing technique, because for the traditional GPR data processing technique, we are totally relying on this surface amplitude. However, now the increase in surface amplitude may not be caused by the density increase. Instead, it might be caused by the water. So we cannot use this single feature to get the density anymore. So we have to investigate another data processing technique. And considering the GPR wave is ultra-wideband, so we transfer it to frequency domain. As you can see, these two figures are the surface reflection amplitude in frequency domain. And this is simply by using the Fourier transform. As you can see, the x-axis is the frequency and the y-axis is the amplitude. And the right figure is just the amplified part of this top part. So as you can see, the frequency components are from 0 to 3.5 gigahertz because it's ultra-wideband signal. And as you can see on the right part, the blue curve is the data collected at dry pavement. And when we spray water and collect data after 1 minute, this red curve raised up. And then when it's becoming dry and dry and dry, it's getting closer and closer to the dry pavement curve. And interestingly, we found that this left part, as you can see here, it's actually all of the curves are overlapped, which means they are not changing. But the high frequency part changed a lot. So as you remember in previous slide, in the time domain, the curve increased a little bit, and that increase is actually accumulated a contribution of all these frequency components. And here we found that most contribution comes from the higher frequency part. So different frequency components interacted different with water, and the amplitude of higher frequency components increased more than the lower frequency components. This can be explained by some EM wave theories, and that has something to do with the relative size of the EM wave, the wavelength, and the layer thickness. When your wavelength is very high, very big, and the thickness is very low, you probably will not see that layer. And when on the other side, if the wavelength is very small relative to the layer thickness, then most of the energy will be reflected. So this can be explained by EM wave theory. And most importantly, we can use this feature. We can extract some feature that is insensitive water. So we want to keep the left part of the frequency components and throw out away all this right part, because these parts are affected by water. So in order to keep that part, we want to use some filter, and we use bandpass filter. First, we have to extract the surface reflection, because we are not interested in anything below the surface reflection, as I mentioned before. And we apply a bandpass filter. For example, I can choose the bandpass filter is like this kind of filter. And we'll only keep the frequency components between this lower cutting frequency and higher cutting frequency. Anything outside this region will be thrown out. So we need to investigate this feature extraction method because we don't know what cutting frequency we want to use and what cutting frequency give us optimized result. So after applying the bandpass filter, the surface reflection will be reduced to a smaller value because we're throwing out a lot of frequency components and only keep the frequency components within this region. So we can use this amplitude after filtering as our feature value because we know it's sensitive to the density, but it might be less sensitive to water. So we keep changing the cutting frequencies, and we found that, and we can plot them versus time. And here's the final result. This x-axis is the time after spraying water. So the higher the x value is, that means it's closer to dry pavement. The y-axis is the reflection amplitude, and I normalize it to the data on dry pavement. And as you can see, the original data without any filtering, without any data processing, is this blue dot curve. As you can see, the surface reflection amplitude of original signal increased by 6.2 when you spray water. And when the water evaporated over time, the surface reflection amplitude would be reduced to reach 100%, indicating the pavement became dry. And when you apply a bandpass filter, for example, from 0.2 to 2 gigahertz, which is this cross line, and you will find that the change in reflection amplitude after spraying water was smaller. And finally, we found out optimized cutting frequency, which is from 0.2 to 0.8 gigahertz as the cutting frequencies. And we found that the feature value stayed around 100% regardless of the water amount, suggesting that this feature is insensitive to water. So this is a very good feature because no matter how much water you spray, as long as it's within that range, it will be not affected by the water amount. So we use this algorithm to some field project, and we also developed this. We also modified the GPR antenna setup to be applied in the field. As you can see, this is our standby position, which means that before compaction, the antenna was lifted up to vertical position to avoid any disturbance to the compactor. And when compactor passes, the antenna was lowered down to horizontal position to collect GPR data. So in that case, we can collect the GPR signal reflected by the pavement after each pass and at the exactly same point. Please, it should be noticed that this setup is very temporary setup. It's just for research purpose. In the future, we can incorporate this to integrate this GPR antenna with the compactor, so we can do continuous measurement. And I want to show you how this data processing technique gonna change the result. So this is a figure I showed you before. As I said, when you apply this data processing technique, this amplitude is gonna decrease. And this is the result of the compaction curve. X-axis is the passing number of compactor. The y-axis is the feature value. And as I said, I normalized it to the zero pass, which is the original one. And as you can see from both of these two curves show the similar trend. The blue curve, I should have explained this before. This blue curve is the normalized maximum amplitude. Basically, I'm extracting the value of this. And this red curve is the reflection amplitude after the filtering or after the data processing. And as you can see here, both of them show the similar trend, which is for the first couple of passes, the density increase is dramatic. Almost the density increase is finished within the first couple of passes. And after, let's say, 4 passes, this increase becomes gradual. However, if we don't use the data processing technique, this curve, the trend of this curve is partially contributed by the water. And if you use this data processing technique, this effect of water can be eliminated. So this curve is kind of closer to, is totally affected by density change without the effect of water. And we apply this method to, this is 3 projects. And the data was processed automatically in real time using software developed by us. And all these 3 figures show the similar trend, which is the asphalt concrete density increased dramatically in first couple of passes. Then the increase become gradual. And then after the construction, so we want to apply the GPR method both during the construction and after the construction to be a complete QC/QA process. So after the construction, we also did a thickness and density prediction, and this can be done pretty quickly. As I said, it can be done, collect data at highway speed. So we can get the thickness profile and density profile and the alveoid profile. These 2 curves are 2 locations because we have 2 antennas and we scan once, but it scans two lines. So as you can see, the thickness is between 2.5 to 3 inch, and the GMB is between 2.3 to 2.4, and this is alveoid content. We want to do some validation. However, the 3 projects doesn't allow us to take course because it's newly constructed. So we compare our data with the nuclear density gauge, and we get 6 test locations. And we found that the average difference between the GPR predicted density and the nuclear density gauge predicted density is around 1.1% averagely. But this is not the relative percentage, this is the absolute percentage. So findings, the spectrum analysis of GPR surface reflection amplitude after bandpass filtering is insensitive to change in water quantity. And it can be successfully applied for real-time compaction monitoring during construction. It can be applied to predict asphalt pavement layer thickness and density profiles after construction also. And it's continuous, it's rapid, it's non-destructive, and the data processing can be done automatically by using the software developed by us. And we found that the density data was comparable to density values obtained by nuclear density gauge. Acknowledgement. I would like to thank the input of Samuel and also assistance of Jim, Aaron, and James. And also I need to thank Jaime to help me to collect the data. Thank you. Questions? Yes.
When you said density, it's the average density of the entire asphalt layer you are talking about?
Yeah. No, actually, because we are talking about the new construction. So I consider the top part of surface layer is represents the whole asphalt layer. It's not like old pavement.
Because if the thickness is large, then you tend to have a gradual density.
Sure. Okay. But this method can only measure the top part. Okay. There's a terminology, or there's a parameter called penetration depth, let's say, or surface depth, sorry, in EM wave theory. That means to some point that means like to some point that's the range of the material that affects the GPR signal. So I think it's around I didn't calculate that, but it's I would say it's around like 2 or 3 inch. No, maybe, yeah, around 2 inch.
Second question is that when you used the filter, this bandpass filter, it appeared that you did it as a trial and error basis. That
no.
means
Do
you have a theory to predict that what should be the filter range, the frequency range you should use as a filter, so that the effect of water can be eliminated?
Do you have a theoretical backup to support this trial?
Well, actually, as I said, this is actually an ideal bandpass filter. In reality, there are several types of filter. For example, the finite length filter called FIR. I use the FIR. Not the other type is infinite length filter, is IIR, and this is ideal band pass filter. You cannot achieve this. Actually, there will be a lot of ripples.
True.
So.
True, but then I'm talking about the F1 and F2, FK or something.
FH,
FH,
which means high.
So is there any way to theoretically determine that this is my frequency range which I should use for my filtering purpose so that I can remove the effect of water?
Water.
Probably you're working.
I don't think there will be a theory to deal with that. As I can, actually, that's the purpose of this investigation. And I did that. I answered this question by doing the test. So finally, I found that by using this, it's stayed around 100%, which is insensitive to water.
But in principle, should we not have a theory to be able to do this? Because we know the dielectric constant of water, we know the thickness and then the asphalt layer, and if we know everything, we can simulate the electromagnetic wave penetrated and getting reflected.
That's a very, very good question, but this doesn't apply for this application. The reason is you don't know how much water you sprayed. So when I tackle with this problem, when I try to proceed with this problem, there are two approaches I can go. First is I want, as you said, I want to develop some theoretical things to eliminate the water. But by doing that, you have to know exactly how much water you sprayed. So I go to another direction, which is no matter how much water you spray, you always need to eliminate the effect of water. So as you can see here, at zero time is when you have the biggest amount of water, and when at, let's say, 45 minutes, it's close to dry. And within this range, you always have like varying amount of water. So you cannot use kind of theoretical thing to deal with this problem. So, yeah.
Just to follow up on that, I have a question also. Now, I understand you're dealing with surface reflections, right?
Right.
And that's the surface, the lift, the top lift you're trying to get the density from. But also, we know that the different antennas and the different frequency antennas generating EM waves have different depths of penetration, which you also mentioned.
Mm-hmm.
And usually that the higher the frequency is of the antenna, the shallower,
right,
that you're doing much better, more detailed scans,
mm-hmm,
correct?
Right.
Some of these frequencies, do they link with the depth of penetration ever? Or this is something different, the frequencies you're doing?
Well, as you said, the lower frequency usually have larger wavelength, and it can penetrate more. And here I'm using that theory, which is for larger wavelength or lower frequency. It's not only penetrating more, it's also insensitive to a lot of things. It's insensitive to small stuff, just like just like if you want to detect some very small stuff, and if you use a very high lower frequency and higher wavelength, you are not going to see it. Like for finer detection, you want to use higher frequency.
Right. In a way, I think you confirmed what I was saying.
Right.
With lower frequencies now, which actually go deeper, deeper penetration,
mm-hmm,
that makes it less affected by the surface moisture.
Yes. That's the maybe it's the same theory but a different explanation or different perspectives.
Different. At least my mind was working.
Okay, can I have another last question?
Yeah.
You gave a formula for GMB calculation.
Yes.
Can you throw some light on how that formula was derived?
Was what?
Yeah, it is like purely empirical or?
Oh no. It's totally based on it's like MEPDG. Okay. It's partially theoretical, partially empirical. The theoretical part is there are EM mixing theory, which there's nothing to do with the GMB or this called the GSE is I think the density of the aggregate. It only tells the EM mixing theory is only telling us like you have this portion of, you have a big mixture, and the mixture has, let's say, 3 phases, and each phase occupies a certain amount of volume, and each mix has a dielectric constant. So tell me what's the total dielectric constant, or the effective dielectric constant for the whole mixture. So that's what EM mixing theory tells us. And then we apply this theory to pavement, because so then we introduce these these parameters.
Does it look like a weighted average, or it's more complex? Weighted average means volume into dielectric constant
Plus volume into dielectric constant.
No.
And divided by all the volumes.
You want to
Sorry, as I understand, that's also the ingredients. Like in HMA, there is the aggregate component, there is the binder.
Right.
B stands for binder, SC or S stands for aggregate, right? As
Yes,
I remember from
yes.
Zen's original
Yes.
work. Yeah, right.
And that's derived by strictly theoretically derived. And why I say there's some empirical part is there's a value here. Okay, let me see. Okay. Sorry, this equation have already eliminated that empirical part. There would be a the reason why I say that is when they derive the equation or EM mixing theory, they assume all the particles within that mixture is sphere. So in our case, we need to kind of input a kind of shape factor, and that shape factor is arbitrary. And that's the empirical part, but it's not reflected in this equation. But as I said, this is partially theoretical, partially from experience. Yeah.
So before you go to the field and apply this technique that you developed for processing the data, you had a small study here to spray the water on top of the pavement, and you built your data collection technique based on that study, right?
Mm-hmm.
So in the way that you spray the water on top of the pavement, was that really simulating what happened in the field? Well, my question is that, what if you have water inside the material as opposed to just on the surface?
Well,
the
yeah.
water is mixed with the material. If the data is the same, I mean, my question is that you have different mixtures. Like you have warm mixed asphalt, you have SMA, you have like dense HMA. I mean, are you gonna use the same technique for all of these different
Well,
mixtures and different situations?
Very good question. But I have to understand that like step by step. First, if you are talking about when we talk about moisture is a very complex problem. Like you have different shapes of format of moisture. If we are talking about some moisture totally mixed with the asphalt mixture, or it's totally saturated mixture, there's no way to deal with that. There's no way to you can like still get the density, as far as I know. But here, fortunately, we are talking about some moisture on top of the surface, and because in the construction it's very hot, and it's evaporating very quickly. I would assume there would be no, if there's any, there's not much, but I assume there's no moisture inside that mixture. I assume that top layer, the top part of the surface is moisturized. Let's say around that's 1 centimeter. Actually, I'm doing some finite difference time domain method to simulate this, but that's the problem I consider. I'm not considering the anything like saturated asphalt, because that's the dead end for GPR study. I will not.
Just to add to that, actually, remember he's trying to simulate the effect of the water coming from the roller, because the roller compactor is for adding that water on the surface. It's basically that's how water is generated on the surface. He's basically studying that.
Yeah, and it's evaporating very quickly, and also it's very small amount. If you go to the field and look at that carefully, I think you will get the same conclusion that as me, there will be no water inside. So that's how I can start this problem. If it's totally saturated, I will not touch this topic. Yeah, there's no way. Yeah, so many years GPR researchers have been want to do this, but no way. You might probably you can No, yet, yeah. So regarding your next question, is the algorithm developed based on laboratory tests can be applied to the field, as the field has a lot of variations. Well, this is just a phase 1. And as you can see, I'm only showing you the trend. I'm not telling you, okay, this is like after one pass, what is the density, and after another pass, what is density. I'm not telling you that. I'm only telling you the trend. And that's my next research topic for my PhD. So I'm going to keep it as a secret now. So you can find, in the future, you can attend my final defense, so you can know the answer.
Spoilers, right? Sounds good. Any other questions?
Aaron? Did you?
All right. Thank you very much again.
Thank you.